Okay, question 7 is about isotopes and radioactive decay. So which of these describes an isotope? So if I had two the same, we know that the lower number of the two, and by lower I need the smaller one of the two, will be the same, it has the same number of protons. And we know that the larger number of the two will be different in some way. Remember, sometimes in the exams they flip these round, so always make sure the smaller number, it's not a top-bottom thing, it's to do with the size of those numbers. So we know it's going to have the same atomic number or proton number and a different number of neutrons. So that will be a same atomic number, different number of neutrons. Now we've got a decay where we've got a proton going to a neutron and they're trying to catch you out. So the one I told you about was, I said, we looked at a sex change in terms of the nucleus. And we said, well, one of the decays we've learned is a neutron will change to a proton and emit an electron. But in this one here, we've got a proton changing to a neutron and it's going to emit a positron. So we're after beta plus or a positron. So it's an electron's antimatter equivalent. So Sig, beta plus. On to the next part. Half-life of cobalt-60 is 5 years. It's going to tell us it had an initial activity of 38.5 kilobecquerels. Just check if I need to change it. No, I can leave it as it is because the answer's in kilobecquerels. Estimate the activity. So I've just taught you to start. Sorry, take your initial value, whatever it is. So I'll do something nice and easy. Let's go with 20 and we write start and then we half it and write the half-life, half it again, and we just keep track of those. So 10, 5, etc. I'm going to do that same, but the crucial part is writing start under that one. So many students get caught out by calling that the first half-life and it isn't. So, well, we've got 20 years difference, so we need to find out how many half-lives we need. So 20 years of activity, we're going from the year 2000 to 2020, so that's 20 years of time is going to overlap, is going to elapse. And it tells us that the half-life is 5 years. So 20 over 5, we've got 4 half-lives. So we're going to take the first and write start, and then half it, 1 half-life, half it again 2, half it again 3, half it again. We have done the 4 half-lives that we need. Again, students might make the mistake of halving it 5 times, and then we can just write that down, 2.406 kilobecquerels. Explain what can happen to a person if they've got prolonged exposure to gamma rays. So we've got to talk about the risk, and we know that these are ionizing, as they have a high frequency, very high frequency, so a loss of energy. And then we're just going to talk about that lead to damage to the DNA and then lead into tumours, cancers, things like that. So gamma rays are ionizing and they form positive ions. Every time I'm trying to give the model answer so that the same repetition of those answers is pretty fluent. These positive ions damage DNA or cells. This can lead to cancers or tumours, which is uncontrolled cell growth. On to the next one. We've got a GM tube, so a Geiger-Müller tube is connected to a counter. The teacher places it near a radioactive source. The student starts the counter and a clock at the same time and writes down the readings shown every 50 seconds. Calculate the average count rate in counts per second. So ultimately, let's draw the area, and we want this change and that change, and it tells us we want counts per second. So this is going to be change in y over change in x. You don't need to calculate a gradient, it's there. And a good tip is you're going from this point here, use your line of best fit, don't use that point there. Okay, you can see they're giving you a line of best fit for a reason. If you do that and use that, you will get the wrong answer. So we are going to this point here ish. Okay, so going into the question, I've already looked at it, you know me, I've got astigmatism, so it makes it tricky. 1720 divided by 120, it is 14.3, and the mark scheme says anywhere between 12 and 16. So I was quite proud of myself in terms of using the graph properly. The student says the experiment must have been done carelessly because the data seem quite scattered. The teacher claims you should expect this, and you should. I taught you RS done. Radioactivity is the random and spontaneous decay of unstable nuclei, and it's this key bit. It's random, and because it's random, it's not going to follow some beautiful pattern. It is just that data is random. So the random decay, radioactive decay, is random and spontaneous process. Therefore, there will be variations in the reading because it's random. The end.